Well, good morning, and it is 6:30 in the morning for me, everyone. So please excuse me. I'm going to be drinking this large cup of coffee. Um, and because of the timing, I couldn't attend the rest of this meeting, but I did look at what y'all were talking about, and I do think hopefully what I will talk about will be a good culmination to what everyone has been thinking about the last couple of days. And I'm really actually quite disappointed that I couldn't attend the rest of the meeting because when Fiona and Stuart approached me about this talk, it was really exciting for me. One, because it said to me that our community cares about sharing and reproducing and how do we manage codes for our community. And this is like a really important topic for me, something that has been I've been working on my whole career, and it's taken me a long time to get to a lot of the ideas I have now. And I'm really excited that people would want to hear about these things. That being said, this is the first time I've given a talk like this. So if you can give me some grace, I may have some stumbles. This is a totally brand new talk for me. So I will explain this very goofy equation title in a minute. First, of course, I need to recognize that we have received funds from the National Science Foundation to make many aspects of my science happen. And this is, like all science, not work that was done in a bubble. And I've had a lot of inspiration and collaboration with many amazing folks. And included on this list is my current graduate students at Tulane, but of course there were many who also came before them. Okay, so we're gonna start this off. With a little thought game. Okay, so I'm going to ask you a bunch of questions, and because of the Zoom format, you won't have to necessarily answer them out loud, although you can answer them out loud, that's okay, but mostly we're just going to walk through them and think. So, have you ever had trouble running the computer code that came with the published paper? So maybe you read a paper, you were super excited, and they actually had a data repository and a code repository. So you went and boom, you couldn't even probably get off on step one. And I am posting this because I was going to dig up some of my old, really, really ugly codes. But of course, Stack Overflow did not disappoint as usual. And I personally got a big laugh out of this when I saw this. My eyeballs just died as a variable. I've definitely done stuff like that before. And please excuse the memes. There's a lot of talk in this. There's a lot of words in this talk, and so I've tried to pepper in memes because I really love memes. But yes, pretty code and ugly code, or the lack of pretty code, I should say, is one reason why we can't run other people's codes. But there's a lot of reasons behind that we'll start to discuss today. Sometimes maybe you are a modeler and you have a lot of experience with one particular piece of software, but you read a paper and they did something you thought was really cool. So you're like, I want to build on that, but I'm going to try to do it in my own software. And then somehow you got totally different results. What about if you just tried to change a parameter from what values were published in a paper, and all of a sudden, like, you're like, that's not a landscape, that's a donut or something like that. And then you've probably been like, why is this so hard? And if you answered yes to any of these questions, you are in the company of me, because all of these things I have experienced, okay? So we're going to try to tackle and break down some of these things throughout this talk. So there's a lot of different ideas here, and hopefully they'll string together to my vision of what I feel is really necessary for us as a community to do this. This is not one person's job, but it's really the community's job to come together around these ideas of reproducibility. The last question I'm going to ask is one that came up for me just about a month ago. I was at a conference for scientific code developers, academic software developers. And there was a room of about 300 people. And I walked in and I was like, oh, I felt like I'd gone 25 years back because it was kind of like when I started out my PhD and I was always the only woman in the room. It turns out software is not nearly as, I would say, diverse as geomorphology, which is saying something. And so I like to start off with a nice reminder of equity or the lack of it. And I love this quote from Marian Wright Edelman. She was an American advocate for children, for both education and healthcare. And she said, you can't be what you can't see. So if you don't see yourself in the room, it's oftentimes to feel like you belong. But I want you to know that you do belong. And I hope that I really do think part of equity is open source. And that is something I really feel strongly about. So hopefully I'll bring that into this talk as well. So some of my goals for this talk. First off, like everything, I always want you to feel welcome. And I know it's a little bit odd in the Zoom space, but hopefully this will be an inclusive talk. I hope you can walk away with a deeper appreciation for what it takes to maintain community software and how important community software is in reproducibility. And then finally, you'll walk away with maybe a little bit of motivation to collaborate and contribute to this community. And there's many ways that you can do that. And I will talk about that throughout the talk. So we're going to start off with this very goofy thing, and we're going to end with it as well. And so I decided to call this my academic software hypothesis. And my idea is that if a community decides that numerical modeling results should be reproducible, then what do we need to do as a community? And what we need to do is, first off, value reproducibility. Okay, no one in science is going to do anything if it's not valued. That is, if you can't write a paper about it, and papers are currently one of our, biggest ways to show that we are productive, we're not going to do it. We have to agree on things as a community, because if we want reproducibility, we have to come up with standards. And without those standards, which is what we have right now, we kind of just do things here or there, and there's no real connectivity amongst our reproducibility. And we also have to train people to use these models. If we want people to be able to reproduce numerical modeling results, people need to know how to use models. And part of this, I really feel that open source is very deeply tied to reproducibility. So we have to both maintain open source software, and we need to value the work that it takes to actually produce this software. And what that means is we need to give people credit, and we need to give people money. So what we're going to talk about first is open source software. Second, we'll talk about what I think reproducibility means. And actually, I move this around a little bit. We'll do training second, and we'll do reproducibility third. Okay, so some questions we're going to explore, and we'll touch on all of these throughout the talk. I'm going to talk about what I think model reproducibility is. But again, I think this should be a community effort. So this is not just Nicole's vision. We need a community vision. What do geomorphologists need to know before running a model? Who's responsible for teaching this? And again, all of these questions are going to be not with one answer, but many answers. Really, I should reword this and say, why would you want to share and make your software open source in the first place? And there are many reasons, even though it is a little bit more work. What are you responsible to the community? If you make your software open, what do you owe the community who's using that open software? And how can we make academic software more user-friendly? Because if we want to do reproducibility, we need more people using codes, and then those codes need to be more usable. And finally, what is sustainable open source software? Because that is an idea that has been pushed, at least in my funding community, a lot. And I have a lot of strong feelings about it. Okay, so now let's get back to this very funny, or I thought it was very odd, maybe title, but I couldn't think of anything that really summarized what I wanted to talk about today. So I made this little equation because I'm better with equations than words. And so what does this mean? Software plus data times people. So behind everything we do is people. So there's no software without people. There's no data without people. And oftentimes it's from data that we are motivated to use software or create software. But all of this happens because of this very big cog, which is people. So there's people behind all of this. And if we're not working together, everything stops, right? The whole machine stops. So I tried to make a little schematic about how I view the whole open source ethos of academic software. And I'm going to touch on this generally as software, even though my talk was on the topic of numerical modeling. So you're going to see there's probably some overlap in what Wolfgang talked about this morning. So let's start off from the view of the software developer. So here's a software developer, and they get an idea. And oftentimes our ideas come from data. So in my case, a landscape evolution modeler, I'm looking at Google Earth or whatever it may be, walking in the woods, and I'm questioning, why is the landscape this way? And I want to understand it. And for me, one of the tools that I use to understand it is a numerical model. And so I'm inspired and I start writing up my code. And I put this as a two-way arrows because I'm writing the code, I'm editing the code, I'm debugging the code, I'm improving it. And as that code starts to work, I feed it data, I produce data. And this is a really iterative process because as you start to produce data, you may need to tweak your code. And of course, that data oftentimes need to be interpreted. And so you build software to interpret that data. Sometimes the software for data interpretation is built into the numerical modeling software. Sometimes it's not. But you can see this is a mini feedback loop. And so I'm doing all of these things. I'm coding, I'm making code, I'm creating data, I'm figuring out cool ways to visualize it, which gives me more ideas, and so on and so forth. And I'm working in my own little bubble. Okay, but then some users come along. And in this example, our users are going to be people who are not expert coders. So they're not at the level where they're actually going to be developing their own models. And users too, they're geomorphologists. They go out, they're in the wild, in the field, and they're inspired. And they say, I want to learn more, just like the developer does. And so they want to run some software. So in this case, they're using the software. They are not, it's a one way, and I'm not quite sure if the arrow should go this way or that way, but there's a one way. Okay, so these are not users who are going to be editing the code, but they will produce data and they will need to interpret that data. So they're using the software. So we have the developer and we have the user, and obviously the developer is also the user. So what happens when the user is confused? So the user is confused, they have questions. Sometimes these are really technical questions. These questions might be, you know, I can't install the code, I can't compile the code, I can't run the code. I hit go, and 2 days later, I come back and nothing has happened. This is one set of questions that the user may have. Another is sort of more on the sciencey side, like, you know, I'm changing the parameters. I don't really understand why things are changing. These results don't make any sense to me. I'd really love it if you had just like one different way to route the flow on this model. Okay. So the question is, what happens when users get stuck? What does the software developer owe to the users, if anything, right? And if it's open source and I've done this for free and the users didn't pay for the software, well, I've already given them something for free. So why should I give them more free by giving them my time and answering these questions? Okay. And so this is really a philosophical thing. Should we actually, how do our communities work together? How do the folks in our community work together? Okay. And so I divide these questions up into two different sort of bowls. The first bowl is the technical. The software just isn't working. And so that's one set of questions. But then there's the other questions about interpreting or adding. And I think for me, I approach both of these things differently. And I think it's something that we want to think about. Okay. So what I'm going to do is I'm going to use the example of Topo Toolbox, which is, for me, this is what I would call a community code. It's open source, and it is a great example of what I think community codes should look like, and an illustration of how users and developers work together. So I think if y'all were here this morning, you heard Wolfgang maybe talk a little bit about Topo Toolbox, but let's just use this as sort of a scaffolding to start our discussion. So Topo Toolbox, here's, if I Google Topo Toolbox, here's what I come up with, this beautiful web page. And the first thing I see, for me, the first thing I see is, okay, there's directions on how to download and get this data. Cool. And it's open source. And look at this, downloads, getting started. I feel great. I actually can hopefully install this software. Now, what if I want more information about how this works? I'm going to click on this Topo Toolbox button up at the top. And wow, to me, okay, this is really good. So what I'm going to show you here is, first off, there's documentation. And so here on the web page, there's information about how you can actually run that documentation. Okay. Sorry, everyone. I just got a little bit, things were in front of each other. Okay, what about if I'm running the code and something breaks? Where can I report bugs or suggestions? That is a really important thing. And that's that feedback between the users and the developers. And there's information on that as well for Topo Toolbox. And then finally, what if I'm just completely stuck? Amazing, we can actually access the developers. And so if we hit on this right here, this Git discussion forum, it takes us to this page. And this is a place on GitHub where you can actually ask questions. So you can see someone here has said, how should I route the runoff on each grid to the watershed outlet? So this person is a user and they were able to submit a question and then get an answer from the developers. That is gold star. That is A+. And also that's a lot of time from the developers, but it's really great because it means more people can probably access and use this code. So I call Topo Toolbox community software. And here's some of the things that make community software. And this is all, you know, in the world according to Nicole. It's open source. You can see the code if you want to. There's documentation, as I've just showed you. There's directions for downloading, installing, and using. And there's also an active discussion forum where not only can the developers talk to the users, but the users can talk to the users, and users can search that forum to maybe get answers to questions that people before them had and now. And there's even more. Okay, so I'm going to highlight this. First, I'm going to highlight TAC, which was developed by Adam Forte. And so TAC is a topographic analysis kit, and it's actually built on top of Topo Toolbox. So it takes advantage of some of the structure of Topo Toolbox. And when I Googled TAC, I came up with this web page, and I just want to highlight this first thing that's written here because it's like Adam was channeling this talk when he wrote this. He says reproducibility is a critical component of good science and is aided by easy to use, well-designed, and open source tools for complex analysis. Reproducibility goes hand in hand with open source tools, okay? And that's why we need to talk about these two things closely together. So if you think that I'm going off the rails here, this is not just me who has these ideas. So what about TAC? Is TAC open source community? Is TAC open source software? So look here, we have a link to the GitHub repository so we can see the code on GitHub, and then there's a README, and amazing. There's an error reporting and feature requests. There's information on using this. So this is, again, another piece of open source software that is built on top of Topo Toolbox, which illustrates the real advantage of developing open source software is that it can kind of explode like a network. So thank you to Wolfgang and team and Adam for building and maintaining community software. And so the question is, why do they do it? And maybe it's because they love the work, but it turns out usually good work is rewarded with more work, okay? And as much as we all love our science, we all have other parts of our lives that are pulling at us and that we want to spend time on. So we don't want this to envelop our whole life. So what is the motivation? Maybe you'll get more citations, maybe you'll get more money, maybe you'll get glory. But mostly, probably the reason why folks do this, or this is the reason why I do it, is it's something I wanted for myself. And then I realized other people might appreciate it too. So that community part of my head turns on. And I say, let me make this shareable. Okay. And that's really where open source community software starts. And it's true, maybe you will get some more citations and maybe you'll get research dollars. But it's also going to take time, and time is money. Okay. But good things can really happen from this. And so what does it take to get my gold star for community software? One is open source. So you can go out, you can see that code to understand it. There's directions for downloading and install. There's documentation and tutorials, so examples on how to run things. There's forums and mechanisms to ask questions and to report bugs. The code is maintained. And so what that means is that folks are constantly updating that code. So for example, say there's a new release of Python and your code is in Python and some things break, you have developers behind the scenes fixing that code so that it can work as the community advances and grows. And also the community can contribute. I don't know if that's 100% absolutely necessary for community software, but it seems like having methods for the community to contribute, but not just to contribute and make their own thing on the side, but give back, isn't that just the essence of community? And so I didn't highlight it, but also on top of Topo Toolbox is TTLEM, which is a landscape evolution model, and that work was spearheaded by Benjamin Camfort. And so you can see how one thing, if it's accessible, can build many things, and how amazing that is for our community, okay? So if we want to build community open source software, there's this idea of sustainability. So we build it and it's made, but software can't exist in a bubble. Just like everything else, the world evolves around it, and there's something called bit rot, which means if you don't keep updating, your code, eventually it's not going to work anymore. And it's not just that, you're adding on bells and whistles, and as our community figures out maybe parts of the equations we've developed need to be tweaked, the code needs to be tweaked, and so on and so forth. So what does it mean for software to be sustainable? And I feel this is the million-dollar question for so many reasons, because one, nothing is sustainable without money. And I really feel like that's true, because there's time to sustain and time is money. But some things that help behind this, and this is all part of the community source sustainable motto, is you have to use version control. So something like GitHub that allows you to track the evolution of your code. Code testing just means that as you write code, you also write code that will test that piece of the model. And so let's say, Fiona writes this amazing component that can calculate hill slope evolution. And then I want to go and just like add another little extra parameter to it. But when I do that, I break Fiona's code. If that happens and there's a test in place, the test will run, it will say, we can't include Nicole's part of the code in here because it breaks the rest of the code. So code testing is actually a way to make sure that your community can contribute without breaking the code. And that, I think, gives everyone a little bit a sense of relief that they're not going to do something that's going to, ruin everything for everyone. Continuous integration is the idea that we are as we make changes, we continually put them back in the code. And of course, having something like GitHub makes this a lot easier. Training opportunities. And so if you want the community to use your software, you need to train the community. And there's many ways to do this. It doesn't necessarily mean a class. You can have webinars, you can have online tutorials, all of these things. I would say that is part of, if you are really committed to community software, you need to do that kind of training. I would say the ideas of how to interpret the data, and what if you don't understand why the hydrograph looks as it does, or the erosion patterns are as they are. Some of that is more on the science side, and I don't think that's necessarily the developer's role, but certainly the more the developers can participate, the more the community will be able to take advantage. And again, this is time and this takes money. Online hubs and cloud computing are just one of the things that I have loved so much about the last 10 years. That means that we actually don't even need to download and install. And that makes it so much easier for users to actually jump in and use our software. And of course, community buy-in. No one's going to use it if the community isn't interested. And of course, all this takes money. So you can see I'm repeating some ideas here. So how does this tie into FAIR? And my guess is that you have talked about FAIR over the past 2 days. I'm going to use this paper as an inspiration, Barker, Hong, and Katz. But I think the fourth author here, Anna-Lena Lamprecht, is part of Topo Toolbox too. So this is it's all coming together. So FAIR, of course, is findable, accessible, interoperable, and reusable. Excuse me, my Alexa just turned on. Hold on. Sorry about that, everyone. Okay, so when it comes to FAIR, what I'm mostly focusing on in this talk is the last part, the reusable. So if we just look from the Barker et al. Paper, findable, of course, it needs to be easy for humans and machines to find, accessible, retrievable via standard protocols, and then interoperable means software can work with each other. So that is that whole community software bit about building on it, just like Topo Toolbox and TAC and TTLEM all work together. And that's really amazing, that interoperability. But you can see the words standard protocols, described through protocols. Who makes these protocols? It's the community, okay? So community software, to be fair, we need the community designing these protocols. What about the reusability? Software is both usable, can be executed, and reusable, understood, modified, built upon, and incorporated into the software. So this is the continuous integration part, having the testing. So sustainability, FAIR, community software, all of these ideas go hand in hand to make an ecosystem in which we can actually reproduce numerical modeling science. Okay, so my feeling is this is step one for us to move towards really making reproducibility an active part of our community. Okay, so how are you supposed to learn all this? For me, much of this was learned through CSD Mass, which is an amazing community that's open to everyone, community surface dynamics modeling system. And even though I was a developer, I was not really, I would say I wasn't well versed in how to do sustainable coding and make community software until I became part of the Landland project, which I won't talk too much about today. And so I'm deeply ensconced in this. How much do you need to know? So if you're a user, maybe you don't need to know the ins and out of continuous integration and GitHub. Although GitHub is pretty amazing, I highly encourage learning GitHub. But even if you're a user and you're taking advantage of tutorials and you're taking advantage of documentation, but you're not necessarily contributing back code, you might be contributing questions that help the developers debug that code. I would still say it's really a good idea to understand what's behind this. And why is that? Because one, if you're a user and you understand the work that goes behind it, I think one, you're going to be more open to supporting reproducibility. You're going to be more open to supporting community open source software. And maybe you'll reach out and write a proposal with someone who's a developer. And so this is really a community ecosystem, as I'll say over and over again, that I think we all need to participate and we all have roles in, but not everyone needs to know the ins and outs of how to do all of this. I will plug two things. So the next two slides are a little plug for programs that can help you if you're interested in learning. The first one is Code to Communicate. This is an NSF funded project that grew out of the GeoLatinas. And this is for bilingual Spanish and English speakers. And it's really a sort of first level entry into using Python for scientific analysis. So in this class, which is taught in both Spanish and English, use Jupyter notebooks, and you learn about different Python libraries. So if this is something that interests you, we're currently recruiting for our next class of COCO. It's all online and virtual, so I would encourage you to check out COCO. And then moving a little bit forward, many of our COCO graduates move into ESPN. And ESPN is a program that is run through CSDMS that I am a part of, and it is the Earth Surface Processes Institute. And ESPN is for early career folks to advance their research by learning a little bit deeper into what it takes to build numerical models and to use them. And so this is a 6 or 7 day in-person activity that happens in Boulder. And I believe we will start recruiting for this in December. So if that's something that interests you, you probably want a little bit more than a basic Python knowledge, or at least some Python experience before you would step into something like this. But here's where you could learn a little bit about unit tests and continuous integration and so on. Okay. Another thing that I'm just gonna, if you don't know about, I wanna highlight is two journals that I think are great. One is JOS, and JOS is amazing because the scientific community has always used its big commodity as manuscripts and publications, right? And so if you're producing software, that is a product. And it's not like a traditional manuscript, but it's, let's give people credit for it. And so this is a great way, JOS, to give people credit. And it's actually the writing part of a JOS publication is much less than a standard publication, but developing the software so that it is available through JOS is sort of using these best practices that I've talked about already. And so this is a great way for you to cite these pieces of software to give the developers, a little bit of show that you are supporting what they are doing. And what I also really like about it, it's all open source and it has 0 charges. Another publication that I have really loved working with is geoscientific model development. These are more standard papers, but it's a way to illustrate, yes, my model can reproduce benchmarks, and it's a little less about showing new science, but more about showing model capabilities. Fortunately, it's not free, but it is a great way to learn more about numerical models. Okay, so let's do a little quick recap. What is sustainable open source software, and why do I need to know about it as a geomorphologist? I think I've touched on that because sustainable open source software is really the key to reproducibility. How do we make academic software more user-friendly? And that would be, getting the Nicole Gold Star, developing tutorials and documentation, and really supporting the community. What are you responsible for if you make your software open source? And, of course, the answer to that question is up to you. But I think for open source software to really thrive, you do have to work pretty closely with your community. And why should you build anything to share? You should build it to share. I mean, number one, just because being part of a community is a good thing and it's great, and you get ideas from others and they get ideas from you, but also you never know where these collaborations will go, and we all benefit from the work of others. Who is responsible for teaching how to run a model? I would say the technical aspects are from the software developers. The science behind it, I would hope that we as a community could start in our classrooms, teaching a little bit more about interpreting the data and using models to ask scientific questions. What does a geomorphologist need to know before running a model? Well, that I think really depends on what you want to do with that model and where, sort of how deep you want to go. If you are just planning to rerun a code that was provided with a paper, hopefully that paper has explained the science behind it and you can reproduce it. But to run these models, you have to understand the processes and the equations that go into them. And that is, beyond what most developers can really train. So this is, again, a community ecosystem that supports all of us being able to understand these results. And finally, what does it mean to reproduce results? So this is what I was originally asked to talk about from Fiona and Stuart, and I'm going to spend the next, about 15 minutes talking about what I think model reproducibility is. So yeah, model reproducibility, I think, requires community values of it. Okay, so let's go back to Adam's quote. Reproducibility is a critical component of good science and is aided by easy-to-use, well-designed open source tools for complex analysis. It's critical, okay? See this word critical. This is important, and I would say currently our community's approach, and when I say our community, I'm really thinking about the landscape evolution modeling community. It's hodgepodge at best is how I would describe it. So what the ideas I'm going to illustrate in the rest of this talk are a lot motivated by work that I've been doing with Katie Barnhart and Adam Forte. Some of this you can find in this short communication. This is a preprint that was in eSurf. The preprint didn't sit so well with our reviewers, so we've basically overhauled it into something different. But if you like a lot of the ideas that I'm presenting, you can still find this preprint and see the ideas in there. Okay, so here's what I think our community does. We reproduce benchmarks, but we don't have any community standards about what it means to reproduce a benchmark. We tend to reproduce a benchmark with the same algorithm, but we may vary certain things like time step or grid resolution. But we don't tend to reproduce benchmarks using different models. And another thing we'll do is we'll use the same piece of software and we will compare how different process algorithms will shape the landscape and what their differences are. But really, intermodel and inter-software comparison is something that is relatively rare. I'm sorry, excuse me 1 second. Okay, can you do this later?
Well, another grade tomorrow.
Okay.
I know today.
Sorry, everyone, my kid is going to school. Okay.
No.
Okay. Okay, so I would say that we're relatively good at doing these first 3 steps. This last part, intermodel and inter-software comparison, is relatively rare. Okay, so what I mean by that is you take 2 separate models, say TTLEM and LandLab, and you run them in the same way to reproduce the same results. There's a few examples of this, but this is not something that our community has come at. And this is actually important, right? Because if you go back to one of those questions that I asked, which was, what if you try to reproduce results, publish results that you see in a paper with a different model, and you can't do it? What does that mean? Does it mean the published model is wrong? Does it mean your model is wrong? Does it mean neither model is wrong? Or both are wrong? I don't know, right? I don't really know. And that's because we haven't really done this as a community to figure out what it means. So we need to fund reproducibility and we need to publish studies on reproducibility. And it is interesting because in earth science in general, reproducibility has not been something that has been extremely valued. And I think part of the reason why, I wouldn't say it's not valued, it's just not done that much because, you know, if I go all the way out to the Himalayas to collect some data, if I have the money to go back to the Himalayas, why would I want to redo the same thing I just did, right? So our community, for many, many reasons, has not embraced reproducibility. But I think we have an opportunity moving forward. And this whole meeting that has been organized here illustrates that we care about this, okay? And I think we need to set standards together. So you'll see, you know, you're getting the world according to Nicole, but we all need to talk about it. I'm really looking forward to the discussion section about what you all think these standards should be, okay? And this last point also ties into some of the questions I asked before, because if you want to reproduce someone else's science, we really need to provide the information to reproduce their science. And I would bet $10 that many of you have read a paper and you're like, that analysis was so cool, I'm going to do it myself. And then there's just not enough information to actually do it. And that can be said about all types of science in geomorphology. It can definitely be said about numerical modeling studies because I have been there. Okay, so why aren't we doing this in geomorphology? Because other communities do it. And so probably many of you know about the climate modeling community. I mean, there's a lot riding on climate models, but they have been for decades doing reproducibility and setting standards. Here is a great example from the geodynamics people who wrote this paper, benchmarking numerical models of brittle thrust wedges. Now, my understanding and my knowledge of brittle thrust wedges is pretty tiny, okay? But this was led by Susanna Buter, and my understanding of how this work came together was they had a conference and they talked about things and they started doing experiments, and then they realized they needed to explore this a little bit more, so they had a whole other conference. And through that, they developed these benchmarks. And in fact, it's not just with numerical models. They also do some analytical model or physical, sorry, not analytical model, physical models. So models like in the laboratory of wedges. Okay, so here's an example from their paper. I don't know what any of this means. What I can tell you is there are 11 models here. So each of these wedges is a different model, and they're all run in the same way. And what you're seeing is pressure. And you can see, like, you don't have to be an expert on this. Doing the same thing, the exact same thing, the initial conditions, the boundary conditions, and the same exact forcing, you get different pressure fields. I don't know what that means, right? Like I'm not a wedge person, but wouldn't you like to know if landscape evolution models do this? And wouldn't we like to know if it's what it means, right? If this means the model is not, shouldn't be used or can only be used in this way. We don't know that in our community. And so I'm not going to belabor this. And again, this is just another figure of how these 11 different models compare with an analytical solution. So the black solid line is the analytical solution. And I don't even know what these different variables are. But wouldn't you love to see something like this in the landscape evolution modeling community? Look how informative this would be. And it would help you to know, well, in one case, I might want to use TTLEM. In another case, I might want to use LandLab. Okay. So I think that our community needs to set some standards. And what we can talk about and think about are what parameters can be used, what parameters should be used, what are appropriate grid resolutions for different types of models, what time steps and temporal scales apply for different process models. We always should be illustrating that benchmarks are being met, right? And that our modeling scenarios were recreated to meet our community standards. And this is a lot of work, but it's really, really valuable. And I think it could really push our science forward. Excuse me one second. What's up, baby? Okay, thank you. Okay, so as an inspiration for this, in a paper that did a little bit of this, is this amazing paper by Katie Barnhart and co-authors. And I will point out this part of the title, Determining Parameter Ranges for Select Mature Geomorphic Transport Laws, okay? So what does this mean? And I'm just gonna illustrate a very tiny part of this paper. So here's a table of geomorphic transfer routes. So look at these equations. These are erosion and sediment transport equations for hill slopes. And these might be equations that you're familiar with, but what I love that these authors did was they pulled out all of the different parameters, they gave key references, and then, wait for it, they provided the units on all of those parameters, and they provided lower bounds and upper bounds. And so this is something that I think we as a community would need to talk about. This is, if you remember, the title said mature processes. So all of these things have been published already. So when we first publish an equation, it's not even necessarily in a model. So maybe we don't know what the bounds are, but when we put it in a model, at that moment, are we required to give the parameter bounds? We should at least be giving units. We should at least be stating what values we tested. But there's no set of standards for our community. And I would love, if you're interested in this, for y'all to look at this paper, because I think you can take a lot of inspiration from it, or we as a community can. So again, stating initial conditions, that was absolutely in the Buter et al. Paper. Explaining boundary conditions, including time steps. And the reason why I say this, and it may seem so simple, is, and recently I have been interested in doing model reproducibility, and I've gone back to some of the old papers, and I don't even necessarily, some of them don't even state what the grid resolution is. So what we would like is to have some standards so that numerical modeling studies have enough information in them so that you can reproduce them. So it feels like I'm being a little bit negative here. So let's talk about the good things that our community is doing. We are good about reproducing analytical solutions, okay? So this is just one example of many that I could give. This is the space model, which is part of LandLab. And when Shobe et al. put this equation into LandLab, they illustrated that it could reproduce analytical solutions. So this is a GMD paper, and in that they develop the analytical solutions, and then they show in each of these cases, it doesn't even matter what these are, but the line is the analytical solution, and then the model is recreating it. So that is definitely a step one, and we're doing that in our community. We compare different process equations. So for example, this is a paper from Nicole et al. And what this group of authors did was they used different fluvial processes to test which one applied the most to a particular river and real scenario. So in this case, they were comparing a transport limited model with a detachment limited model and different parameters, and they illustrate that one particular set of parameters in the detachment limited realm could recreate this particular channel. So we're good at that. We're good at exploring spaces and processes. This paper by Benjamin Camforts, which uses TTLEM, which remember, built off of Topo Toolbox, is using the same software, but a cool thing that they did was they used different numerical solutions of the same equation and tested how that impacts the solution. And they also tested how model resolution impacted the solution. So again, you don't even need to know what these variables are or parameters are, that they're these different metrics, but you just need to see the analytical solution is this line, and then these different numerical algorithms do better or worse at reproducing the analytical solution. And you can see something that I really appreciate. You even can see the initial condition right here. So that's a beautiful thing. And you can see they tested this with different resolutions. So something that our community is doing great. These are papers that I love, okay? So there's lots of examples. I could go on and show you lots of examples, but we don't have time for it, okay? But we have lots of examples of testing things like time steps and model analytic, can our models produce analytical solutions? But what we don't have is comparisons between different software. So when you start to look in the literature, you don't see that kind of reproducibility in our community. So it's lonely out there, but let's start, sitting in those chairs and making it less lonely. So again, I'll come back to this paper that this preprint that Adam and Katie and I have been working on. And we took one idea for what inter-software comparison could look like. So we were using the child model, LandLab, and TTLEM, and we just came up with some scenarios, and we had all the same initial conditions for these models. We were able to test in these different, so these models operate on different grid types. So some are regular rasters, some on Voronoi, LandLab also has a hexagonal. And they also use different numerical algorithms. So much like that Camfort et al. Paper that I just illustrated, we were able to compare between different modeling environments, so different pieces of software, different grid types, and different numerical algorithms. And again, we should not be the last word on this, but we said, okay, if we give everything the same initial conditions and the same forcing, will these different models that operate on different, that have, say, different flow routing algorithms, and they may have different algorithms or numerical methods for solving the equations that are within them, or they might have the same, but one is in LandLab and the other is in TTLM. Do they produce the same thing? So we looked at this, and this is just topography, right? So this is plan form, and these look pretty much the same, but if you look at the main channel and all these, it's not exactly the same, but these all were started from the same initial conditions and had the same exact forcing. So does that mean anything? Does it even matter? I don't know, but I think that we as a community should make decisions about how we're going to test these models and what we're going to decide is the same and what isn't. we also compared the results to analytical solutions. And this is something, again, that our community is already doing. But we don't have any kind of make sure if you do a model of X, it can reproduce Y. Okay, and we don't know how these different algorithms and different models and different grid resolutions and different grid types impact our solutions. So something interesting we did, and I'll just take a minute to explain this, is time to steady state and landscape response time is something that we as geomorphologists think a lot about. And we have developed analytical solutions to predict how, if you perturb a landscape by changing the rock uplift rate, how that signal will propagate through the landscape. And we've done that analytically by using things like Hack's law. So Hack's law takes a network and it collapses it into 1D. But that's a beautiful thing because then we can then make predictions about how a whole entire watershed will respond to a perturbation. But when we run a model, a landscape evolution model, it's 2D, right? So it's not exactly the same as that analytical solution. So what I just want you to look at here, this is the y-axis here is the ratio of what the time to steady state is if we use a numerical model versus what the predicted analytical solution is. So we use what we measure in the model about Hack's law and the properties of the network, and we predict what the time to steady state should be, and then we model it. And what you'll note is these are all different TTLEM models, and they're different TTLEM models using different time steps and using different methods for predicting steady state. And every numerical model takes longer than the analytical solution, and in some cases, like tens of millions of years longer. And so part of that is because of network rearrangement, which isn't included in the analytical solution. But wouldn't you like to know that if you were using a model to try to understand your landscape and you thought you had some good constraints from geochemistry on the timings of that landscape, wouldn't you like to know how the model operated and compared to the analytical solutions and what time to steady state was dependent on? I think I would. So how should we move forward? What I would love to see is our community coming together and having a vision for how to make software intercomparison a reality. And this really takes input from users, it takes input from modelers to make this happen, okay? And if we come back, if we go full circle and we come to my hypothesis about academic software and making our results reproducible, we need to really agree on standards for numerical models and reproducibility. And we have to maintain open source software because open source software goes hand in hand with reproducibility. And so what you'll see is that I really think no one person can do this. I think this is a community effort. And I'm so excited that some of y'all have made it through this whole talk and maybe have ideas about how we can move this community effort forward. And with that, I will end my talk. Thank you, everyone.
Great. Thanks so much, Nicole. That was really, really thought-provoking. And thanks so much for all the memes as well. I was really enjoying the meme game as we went through. So we'll just take a couple of questions just so that we've got enough time to have a coffee break before the discussion. So the first question is just,
sorry,
first of
Fiona,
all,
can you help me? How do I'm somehow still yeah. Oh, here we go. Here we go.
You get
here
it?
we go. Sorry. Okay, I got it. Thank you.
Can you see the chat and things? Oh, I can read questions out, but
yeah.
Great. Yeah, so the first question is about, I guess, a lot of authors don't make models and data sets available so that we can maybe deal with these issues of reproducibility. So I suppose it's asking how you think we can encourage people to share data and models.
Yeah, so I think It's a good question. I think, for example, my understanding in Europe, and y'all can correct me on this, is that you're required to if anything that's funded has to be open source. Is that correct?
For data, yeah.
For data, yeah.
Yeah.
And so I think one way to encourage it is we don't give people money if they don't make their data open source. And I feel like that's a real the carrot and stick approach, which isn't always the best one. But I do have a lot of empathy for people who don't make their data available, because it's a lot of work to make your data available. And so I think it comes on both sides. One is we have to encourage people to make their data available, and we have to give them frameworks that are maybe a little bit easier to share their data. And I don't know what the answers to that is, what the answer is to that. Some things that I do really like that have been coming online in the last 10 years, like you can get a DOI for your data set. And so you can actually cite a data set. And I think if we as a community start making things like that more the norm, then we'll start to get more credit for doing that sharing. And I do think it does come down to giving people credit and giving them incentive to do these things. But it's a really hard question, and one that I'm not sure I have the answer to.
Yeah, great, thanks. One question from me actually is, have you thought about reproducibility with the same code, but just updating it when you add in, say you change your algorithm and then suddenly you can't reproduce the results of like a past paper or something? Because yeah, I've thought a lot about that and got scared about that.
Okay, so one thing I will say is that if you have and this is something that I have just learned in the past few years, if you have your code tested, so if you build tests into your code so that when you update your code, you'll find out if the test breaks, that's a good way to ensure that you can still reproduce, that your new code will still reproduce old codes. It's not 100% fail safe, but educating our community and how to build new code tests and test their code, fully test their code, is one way to move forward to preventing that. When I go to software conferences, I hear a lot about like, well, this code is always going to work because, I have it in a Docker and it's frozen. The actual version of the code is frozen. And so it's always going to work. And I'm not sure that that's actually true. But that is one way to at least start to ensure that. But we don't want to have to freeze a piece of code and then go back to it, right? And so I do think testing, and also just, I am a software developer, but I'm also a geomorphologist, and working hand in hand with the software developers is pretty important to figure this stuff out.
Great, thank you. There's a couple more points in the chat. We'll finish there for the coffee break, but